You don't all know me. I'm Luke Shamandi. I'm faculty here at NYSER, and I'm just helping with the program. And today we have the second installment of the 21 centimeter, global 21 centimeter signal theory lectures by Professor Kanan Datta. I just wanted to know, does anyone have any questions, or is everyone fine? Any concerns or anything about the lectures or the room, anything else, any logistics? If there are, you don't hesitate to approach us, myself, Tegan, or all the postdocs and students who are helping with the program. Okay, so without further ado, I will hand it over, and we'll break around 11:15.
Thank you, Lee. So, in yesterday second lecture, I started the discussion on Prof 3 stars. Do I need to use it?
Showing 16.
Okay. So yesterday we started our discussion on sources of reionization and cosmic dawn. Particularly started discussing on population T stars, those are the first generational stars. We discussed that population T stars can be formed. So the relevant cooling channel is molecular cooling channel. Now, let me continue the discussion. And what are the conditions on the halo mass that a halo can sustain molecular cooling? So let's discuss that. So, in a paper by Tegmark et al. 19. So, in this paper,
How will you write?
okay. So in this paper, this paper it is written that so inside dark matter halo you have baryonic matter, and initially you can also have molecular hydrogen. So the fraction of molecular hydrogen that a dark matter halo contains, it depends on the mass of the halo. And so they have, this paper actually have found a relation that relation between fraction of molecular hydrogen and the total mass of dark matter halo. So the relation is something like this: if H2 is the fraction of molecular hydrogen residing in a dark matter halo, of mass m can be written as 3.5 10 to the power minus 4 right. So it written like that. Now if you want to know details about the relation, like how this kind of relation can be estimated, you have to go and go to this paper and look for the details. So you see this this is T virial, and there's one-to-one relation between dark matter mass and virial temperature. So if you know virial temperature of dark matter halo, you can directly use that to estimate mass of dark matter halo. So basically, this equation tells you, it gives you fraction of molecular hydrogen residing in dark matter halo, given dark matter mass. Now, just to give you an idea, 10 to the power 4 Kelvin virial temperature, the typical dark matter mass is around 10 to the power 8 solar mass. So that's the typical number. Okay. Now, if you reduce virial temperature, the dark matter mass will also be reduced. Okay, this number is significant because this is the temperature at which this atomic cooling starts. We have discussed this yesterday, right? So basically, this equation can be used to estimate fraction of molecular hydrogen residing inside dark matter halo when there is no negative feedback. So as I also said that if there are Lyman-Warner photons inside your dark matter, those Lyman-Warner photons will actually dissociate some of the neutral molecular hydrogen. Then that fraction will be lower, right? So this is without any feedback. This is just without any disturbance. So now the same paper also gave a relation. So now you need certain amount of molecular hydrogen to start the of 3 star formation. So you need to have some minimum level of molecular hydrogen, and if it is below that, there will be no star formation because cooling will not be efficient. So that critical fraction, if H2 critical. So this is the minimum fraction you need to start the star formation of 3 star formation. And in the same paper, you will find this relation to be like this: 1.6 10 to the power minus 4 1 plus H so this can be written like this. So this critical fraction depends on redshift, as you can see, and T3 is essentially this. So temperature written in units of 10 to the power 3 Kelvin. So 10 to the power 3. So suppose if T is 10 to the power 3, then T3 would be 1. So it is written in terms of 10 to the power 3 in units of 10 to the power 3 Kelvin. Okay, so now this okay, so now this fraction depends on virial temperature. Now, if you compare these two relations, so this is a fraction, minimum fraction you need to start a star from Prof 3 star formation, and this is the available fraction. These two. Different value for different dates. So you choose one date sheet, calculate PVD and calculate parameter. So it is changing with the date sheet. So now I will show you. Yes.
It's 10 to the power of 3 Kelvin, some temperature like
No, so this is just normalized to 10 to the power 3 Kelvin. So let's say your actual temperature is 10 to the power 4 Kelvin. Then T3 is just 10. So instead of writing 10 to the power something, you are simplifying things.
K should not be there. 0.5 should be.
It is limitless.
Yes, I think so. Yes. Yeah, so this is unitless, so it should be unitless. Now I will show you the result on the minimum mass that can sustain this star formation of 3 star forms. Yes, so you can see it. You can see this. Yeah. So x-axis plots redshift, y-axis is various mass, but you just focus on this green dotted line. Green dotted line. It is calculated using these two equations. So as you see, at higher redshift, the minimum mass is smaller, and if you go to higher and lower redshift, it is increasing. So the typical number, you see 10 to the power 5 at higher redshift around 45, and it is around 10 to the power 6 solar mass at redshift around 10. So, so dark matter mass should be at least this to start the star formation, because these are the halos will have enough H2 to support the formation. Okay. Now, I think first of all, T virial will be lower, and also I think density at higher redshift. You have higher density at higher redshift. So the fraction, let's say T virial is less, then this fraction is also less. So that means at higher redshift, lower H2 fraction can start the fraction. But although the fraction is low, but at higher redshift you have higher density. I guess that is the reason. So if you go to higher and higher redshift, the overall density of universe is increasing. So that means the density inside those halos are also higher. the fraction is lower, but since you have higher density, uh, uh, that is actually helpful. So that's what I understand. Okay. Okay. Now, yesterday we also talked about feedback. So this is without any feedback. Now, what happens that these stars started to form and they emit a lot of photons in all wavebands, and Lyman-Warner band that corresponds to 11.22. Yes. That is also TVDL. It should be TVDL. Yes. Yeah. So this Lyman-Warner photon will dissociate the H2, and then fraction will reduce. Right. Now, if this fraction is going down, then no, all are in TV. All are TVDL. No, see, this is fraction of H2 molecule, and this is the lowest limit that can sustain star formation. So, and this is also a function of T3. So T3 is basically TVDL. Like, so all are TVDL because you have to solve these two equations for TVDL, particular TVDL. If they are different, then you cannot solve it. Then you have two unknowns. So this is FTVDL, this is also FTVDL, and you equate them, you find TVDL, so basically root of that equation. Okay. Why TVDL? Why TVDL is increasing over the red sheet? At lower red sheet. So that is, this is what you get from the equation, but what is the physical reason that we have to think about? This is what you get by solving this equation, right? So you see that this TVDL is increasing, and why it is so?
So TVDL is higher for lower density.
Lower density. So it is increasing at lower density.
TVDL is proportional to the over density.
TVDL will be proportional to it is related to the mass, dark matter mass.
Over density. Because
yes,
that is what supports the dark matter.
Mm-hmm.
So because the over densities are growing.
Over density is going is increasing.
We expect the TVDL. The TVDL is giving kind of pressure to support the dark matter.
Mm-hmm.
Because density contrast is more.
Okay, so that
you
might
need more pressure.
That might be. Okay, so now let's try to understand the effect of feedback. So since Lyman-Warner photons are the one which are actually destroying the molecular hydrogen, we need to calculate Lyman-Warner flux, and we can calculate using the same relation as the Lyman alpha flux expression. So we have yesterday we have derived J alpha, that is the total Lyman alpha flux. So we can use similar equation to calculate Lyman-Warner flux as well. So the Lyman-Warner J Lyman-Warner. So that is basically the spherically averaged Lyman-Warner photons, number of photons per unit striking per unit area per unit time, per unit frequency, and per unit solid angle. And that is essentially same as the previous formula, that is Lyman alpha formula. And we can calculate like using this z equal to z t by 4 pi integration over z pt 1 plus z so so this is the same formula that we have derived yesterday. So you can actually you can replace dt with dz. Sorry, this dz should not be there. This dz should not be there. So either you have dt or dz. So you can actually replace dt with dz. Now this is Lyman-Warner photon emissivity, source emissivity for the Lyman-Warner band. And Z is the Z of redshift of interest, and Zm is the maximum Z from which photons higher than Lyman-Warner band can actually can redshift into Lyman-Warner band. And once it becomes any equal to any Lyman n series, then we absorb, so that will be lost. So before that, it can destroy H2 molecules, right? So this is how you can use the same formula, right? So now you can calculate it. Now this epsilon, so how do you calculate this? So this is also very similar expression that you can use. So this is okay. So see, this equation is slightly different than what we have actually derived yesterday to calculate the Combing emissivity. This dm is the mass function, dark matter mass function. So this actually gives you moving number density of dark matter halos in the mass range of m and m plus dm. So this quantity actually gives you that. So, but we are actually taking derivative of this quantity with respect to z. Okay, and now this. Okay, now you see this m dot star, that is the star formation rate inside a star of mass m. So it is the rate of change of stellar mass inside a dark matter halo of mass m. Now we are dividing this with mp, that is the photon mass, and that gives you rate of change of baryons that are inside the stars. Okay, so basically these two quantity together gives you rate of change of baryons inside dark matter. Okay, that are going into the star. And so this ELW, that is the average energy of Lyman-Warner photon. So as I said, Lyman-Warner corresponds to 11.2 to 13.6 electron volt. So you can take an average value to estimate that, and that is around 11.9. It's not exactly arithmetic average, but some weighted average. Okay, and depends on the spectra of the source. We just simply do average, it will not be. So, yeah, it's different. Maybe. Okay, so this is average E Lyman-Warner, average energy of Lyman-Warner photons, and this is the frequency separation corresponds to this frequency. You can calculate nu for this, nu1. You can calculate corresponding nu for this. So this delta delta nu Lyman-Warner is basically difference between these two, right? And this is the number of Lyman-Warner photons emitted per baryon. This is the number of Lyman-Warner photons emitted per baryon. And that number actually is very uncertain. We don't know how many Lyman-Warner photons are emitting per baryon. So we have to assume some model, and depending on model, this number will vary. Okay. So now, so using this equation, you can actually calculate Lyman-Warner emissivity, total emissivity. Now, here we have written M minimum. So M minimum is the minimum dark matter mass that can sustain star formation. Right. So if you lower this value, you will have more number of photons. But not all low mass halo can actually have star formation. So as I said, this green line actually shows the minimum mass, right? So you have to consider those dark matters which are actually hosting the star formation. Now, this is the self-destruction process. These are the halos which are producing Lyman-Warner bands, and they are destroying hydrogen molecules. And since they are hydrogen molecules, they will actually so now you need more massive halos, because low mass halos will have lesser amount of hydrogen molecules and will stop Pop3 star formation. Okay. Let's say if you consider let's say redshift 20, okay, and the minimum halo mass around 2 into 10 to the power 5 solar mass dark matter halo. So they will be able to form Pop3 stars. But now once they form Pop3 stars, they will emit Lyman-Warner photons, and then those photons will destroy H2. So then this fraction criteria that I have actually explained to you. So that halo had this minimum fraction of hydrogen molecules, but those photons hydrogen molecules are bound. So then that particular dark matter halo 2 into 10 to the power 5, they will not be able to form stars anymore because they don't have enough H2. So then this minimum level will be raised. And now if you calculate this constantly, so you just put one minimum halo mass and you get a number. So you can actually calculate this out for different minimum halos, minimum mass, and you can actually solve for the actual lower limit. Okay. So now so this is slightly different. Very similar but slightly different. It is same, but the expression is slightly different. It's not the same. You can, yes, you can. Different forms of the same equation. Yes, it is going up to infinity. Yes, up to very large. The maximum halo you have in your box system. But principally, it is infinity. So all kinds of halos can emit Lyman-Warner photons. If it is as no, this is this one. Okay, I think this is no. So this is wrong. Sorry. This cannot be infinity. This is some z. This is some z. Yeah, some z maximum. Yeah, this cannot be infinity. Yeah, but minimum mass can actually have infinity. Thank you. So that, so yesterday I have discussed it, right? So so let's say you have you have some photon at some rate z prime, and you want to calculate Lyman-Warner band, right? So if it is, if the emitted frequency is higher, it will be redshifted to Lyman-Warner band, and so using that criteria you can actually calculate the maximum z you can. So if you consider, if you take very high z, it will be redshifted below the Lyman-Warner band, and that will not be useful, right? So by that condition you can use it, you can calculate.
Here we have considered within below.
Yes. Yes.
Then maybe we
From nearby stars can also penetrate that,
So
but that is difficult because it has to pass through the interstellar medium. The interstellar medium is optically. So let's say you have two nearby stars. Now you are saying that from nearing stars, Lyman-Warner photons are coming out, and it is crossing the entire interstellar medium and going into the next star. But I guess since it's Lyman-Warner photon, eventually, so they so it becomes Lyman N. When it gets shifted to Lyman N, Lyman alpha beta, then immediately it will be absorbed by the interstellar medium. So it will not be. So I think mean theta is lesser than the interstellar medium distance. That assumption you have to make. If it is not valid, then your whole theory will come. Okay. So so now once you calculate once you calculate this quantity, you can actually calculate T critical. Critical is the critical virial temperature. T critical by 1000 precisely if you calculate, it is around 3.6. Again, I am using another formula. If you want to know details, you have to go to this particular paper to understand this. Okay. Now, due to this Lyman-Warner background, the minimum T virial becomes, you can calculate, and that is equal to this. Okay. So now, as I said, this you can estimate dark matter mass corresponding to T critical, right? So once you calculate this, you can use that value to estimate a critical temperature, T critical. So that is the critical temperature required for star formation. So if JLW is higher, T critical will be also higher, right? Now you can so using this Lyman JLW you can estimate T critical, and using that T critical you can estimate M T critical. So that is the new there is a new lower mass. Okay. Now I have estimated one lower mass using this virial theorem, and this is coming from the Lyman-Warner band. Let's say if it is 0, then this is 0. Then this same green line will hold. But if it is non-zero, then you have some finite value, and if this number is greater than this green line, so that will your lower mass that can send formation will raise. So this is, so you see this plot, this red line. Initially, Lyman-Warner feedback was not that important at redshift 35 or higher than that, but slowly if you just follow this red line, this is coming due to the Lyman-Warner feedback. So this lower mass that can sustain of these stars is increasing. Okay, because of this negative feedback.
It's a bit.
So that will so this is 20, so it is I mean you can calculate it easily. I mean you can normalize it to any value, even you can normalize it to 10, then your this number will be no, so 20, yes, so 20 is important because we believe that star formation starts around that time. Yeah, so typical redshift range is around 20. So I have shown results in the range 10 to 45. Yeah.
So the temperature is a temperature above which there is no star formation.
Below which there is no star formation. Yeah. So if it is below that, then there is no star formation. So if it is less, then your dark matter mass is also less. Then you have less amount of molecular hydrogen, and they are not they will not be able to pull off the baryon enough to start the star formation. From this calculation, yes. From previous calculation, you just take maximum of the two as your lower limit. Okay. A black line comes from the fact that this atomic cooling halo. So for atomic cooling to start, you need higher temperature, 10 to the power 4 real temperature, 10 to the 4 Kelvin real temperature. So that mass is it corresponds to 10 to the 4 Kelvin. So that is the higher limit of this Prof. Star formation.
Atomic cooling is
Prof. Star formation. So Prof. Star formation are important in this in these two ways. So this is just coming from my calculation. In reality, it may not be there, but you have to sacrifice this criteria.
Atomic cooling is effective when the atoms are there, but molecular cooling is effective when the molecules are there. They're not there in 4G.
Yeah. Okay. So any question on this topic, feedback of this star formation, all? If not, then I will move to slightly different topic, and that is the last topic I want to discuss. That is the IgM temperature. So did is introduce that, like in order to calculate 21 centimeter signal, that is differential brightness temperature, you need to calculate Xc, that is coupling coefficient, and also Tk, the IgM kinetic IgM kinetic temperature. Now Tk or Tg, kinetic temperature. So Girish talked about the equation by which we can actually calculate the by solving which we can calculate the ideal temperature. That equation is 1 plus Z Tk. So this term arises because of the fact that so universe is expanding. Everything is, the temperature of IgM, CMB are going down. So this is, if you solve this, so there is no other source, external source of heating. So if you have hydrogen cloud, and that cloud is expanding with the expansion of universe. Now, if you solve this equation, you get Pk is proportional to 1 plus Z square, some constant into 1 plus Z square, and that constant will be set by the initial value. So IgM temperature actually it falls with 1 plus Z square if there is no disturbances, like no external heating or cooling. Okay, and you know CMB temperature is scaled as 1 plus Z. So if CMB temperature decreases slowly compared to the IgM temperature, it is decreasing faster compared to the CMB temperature. Now initially, actually there is coupling between CMB temperature and gas temperature. Initially means at let's say 1000 to let's say 300. Let's say 300. During that period, there is coupling between CMB temperature and IgM temperature through the free electrons that you have in the medium. So as I said that during recombination, universe became neutral, like almost all hydrogen and helium they are neutral, but still you have a small amount of free electrons available, and that small amount is around 10 to the power minus 4. So out of 10,000, so still have this fraction free electron available even after the recombination. Why? Because we have this CMBR, cosmic microwave background radiation. So this radiation is like that. So you still have some very high energy photon, although they are less in amount, but you still have photons higher than 13.6. So that photon is actually that will create free electrons with this fraction. So you can actually, so there is a differential equation, and you can solve it, and you actually will get the number like this. So if you calculate Xc as a function of redshift, so this free electron actually transfers some amount of heat from CMB to IgM. So that interaction term is something like this: 32 sigma T is equal to the power 4 . So this is this interaction term. This is the interaction between ambient temperature and IgM temperature through these residual free electrons. So that actually helps to transfer some amount of heat energy from CMBR to IgM. Now you see, this is ambient temperature, this is IgM temperature, and CMBR temperature is always greater than IgM temperature, because as I said, IgM temperature falls faster than CMB temperature. So this quantity is positive, and so this entire quantity is actually negative. That means it will help to keep the IGM temperature equal to CMB temperature at least for some period of time. So let's say if there is no, so this is Z, let's say this 1000, and this is lower density, let's say 10, and so this CMB temperature falls off like this, 1 plus Z. This is in log scale. And if there is no interaction, IGM temperature will fall off like this. There will be no, it will not follow CMB temperature. But because of this term, because some amount of heat is transferring to the IGM temperature, so this IGM temperature will follow CMB temperature at least up to let's say 300. At least so the CMB temperature and IGM temperature, T gamma and Tk, they remain same up to let's say 300, because this transfer of heat is very efficient up to 300, and it depends on the factor like Xe, yeah, all these factors it depends on. Okay, but after that, after 300, this process becomes inefficient. It is not able to transfer sufficient amount of heat energy to the CMBR. So then after 300, IGM temperature falls as 1 plus Z square. Not from the beginning, but much later. So I can show you a plot on that. Yes. See, so this is x-axis and y-axis is temperature. This blue line, straight line, that is CMBR temperature, and this red line, you see this red line initially, so this let's say 1000, it remains same with the CMBR temperature up to let's say 300, and then again it falls because the term is efficient after at lower density. Okay, so that's why otherwise you will see much colder IGM if that process is not there. Much colder IGM than we actually see it. Okay, so that is one process by which you can actually transfer some amount of heat from CMBR to CMB. Then there are several other possibilities, like when you start forming stars or black holes, basically quasars, and there can be many other sources of heating like primordial magnetic field or soft heating. All kinds of proposals are there. So those processes are active during cosmic dawn, when you start the star formation, because those are the so these photons from those sources, X-ray photons basically, they can heat up the intergalactic medium. Okay, so now how? Because X-ray, when you have X-ray photon, so we know X-ray photon has, they are very energetic, like it can have energy more than 100 electron volt, right? One X-ray photon. Now you need only 13.6 electron volt energy to ionize one hydrogen. So it will hit this X-ray photon will hit one neutral hydrogen atom. It will ionize it, and for that you need 13.6 electron volt energy. Rest of the energy, it will be transferred to the free electron and proton as heat energy. So out of 100, this amount will be used for ionization, and rest of the energy will be used for heating. So by that process, you can heat up the intergalactic medium. So you have to add one more term. That is okay. So that is 2 mu m p So basically, you can take sum over this gamma x. So this gamma x is all other heating sources. So if you consider x the heating, so this gamma x actually it is defined as the amount of energy being used per unit Kelvin volume for heating the intergalactic medium. Per unit volume, per unit time, the total amount of X-ray energy being transferred to the intergalactic medium for heating. Okay. So now these all other quantities are basically constant. This Hubble parameter and baryonic density, and this is mu. Mu is essentially effective mass. We have helium and hydrogen both in our universe. So the effect. So although hydrogen, so this effective mass will slightly increase. Then this value of this I think 1.3 instead of 1. If you have only hydrogen, then this factor will be 1. But you have helium and hydrogen both, so that factor will be a little bit higher than 1. Right. Now this for X-ray heating. If you assume that stars are the only source of X-rays, which is actually wrong. There are many other sources of X-rays like quasars and X-ray binaries. But if you assume that stars are the only source which is emitting X-rays, then actually you can calculate this number very easily. You can connect this number with the star formation rate that we have already discussed. So this is basically FR, FXC, EX, and then star formation rate density. The same star formation rate density that we used for calculating the Lyman alpha background, Lyman Warner background, the same star formation rate density can also be plugged in here and calculate the X-ray energy deposited in the intergalactic medium. So what is this? This EX is the this is the energy emitted in the form of X-ray per unit baryon. This is the energy emitted per unit baryon in the form of X-ray. Now, out of that X-ray energy, only Fx fraction that will be used for heating, right? Okay, no, not this. So this is the escape factor, X-ray escape fraction. So as you know that stars are found inside galaxies, but we are interested in the intergalactic medium signal. So those photons that are forming inside stars, they have to come out of the galaxy, hosting galaxy. Otherwise, they cannot heat up the intergalactic medium. So intergalactic medium is the medium in between galaxies. So those X-rays they have to escape from their host galaxy so that they can actually contribute in heating. So now not all X-ray photons can come out of the galaxy because they will scatter around or they will be absorbed. So only a fraction of X-ray photon can come out, and that fraction is Fx. Now this is very simplistic model. Of course, there are. It's not that simple. It can be mass dependent. It can be. It depends on redshift. But for simplicity, to understand the basic idea, we have just assuming it to be a constant. And this is a fraction of total X-ray energy that is being used for heating. As I said, X-ray photons actually it used up for ionization. It is used up for secondary. It is used up for first primary ionization. It is used up for secondary ionization and also heating. So that total energy is distributed in different processes. So this Fr is the fraction that is being used for heating only, and that is around 10%, 20% depending. So various people use various numbers. Okay. So you can actually directly calculate this. Now I will show you a plot. Yes. So you see again the same plot. X-axis plot redshift, y-axis temperature. This dot line, black dot line is the CME temperature. This red line, bottom red line, they are basically IGM temperature. Now you see up to redshift 25 or so, they are just following 1 plus z square relation. They are falling off as 1 plus z square because there are no sources, no X-rays, so there will be no external heating. However, first sources starts to form around redshift 25 or 20, and then they will emit some photons, X-ray photon, and so this IGM temperature is going up. This blue line, if you yes, so if you just follow the blue line, blue solid line, that is the X-ray heating. So it is actually the IGM temperature is rising up very rapidly. So you see up to this point there is no heating, but then let's see, this is I think around let's see 15 or so, 16 maybe, and it is because of the X-ray heating this temperature is rising slowly, and then it is actually crossing the CMB temperature at some point. It is crossing the CMB temperature and it is going above the CMB temperature. Now, as I said that spin temperature will also follow the IGM temperature at later stage of reionization. Because of the laminar coupling, they will be highly coupled. So spin temperature, that is the red, that is the dashed blue line. So initially they are going down, but then when the heating starts, it will is also going up. So spin temperature is going above the CMB temperature, and you will see the signal in emission. So if you remember the formula delta TB, the quantity of interest, it becomes positive when spin temperature is higher than the CMB temperature, and that is exactly what happens after some, let's say after redshift. So it is crossing in this model. It is crossing at redshift maybe 13 or 14. So after that the signal, so below 13 the signal will be seen in emission, but higher than 13 signal will be seen in absorption. So the sign change. So delta TB will change its sign at redshift 13, and that of course it is model dependent. It depends on what kind of values of this you choose, but within reasonable parameter that comes out to be like that. Okay, so there are a few other curves. Let me explain this spin temperature curve. So spin temperature, so as I said, spin temperature, during the dark age, collisional coupling is important. So during collisional coupling at redshift around let's say 200 or 300, IGM spin temperature, actually this dash line, this red dash line actually is spin temperature. So this red dash line actually is following IGM temperature, the solid red line, right, initially, and that is due to the collisional coupling XC. The hydrogen collides, they collide with themselves, and that actually makes this spin temperature coupled with the IGM temperature. But later coupling becomes inefficient because temperature and density both they are decreasing. So this coupling becomes inefficient. Then radiative coupling due to the CMB photon, that becomes efficient. So then spin temperature catches the CMB temperature. When radiative coupling is important, it will make the spin temperature equal to the CMB temperature, right? That's what we have discussed yesterday. So then this line actually is catching the CMB temperature. Okay, so initially collisional coupling, then radiative coupling, but then again we start forming stars, galaxies, stars inside galaxies, or maybe black holes, and a liner of the photon from those actually those sources actually tries to couple the spin temperature with the IGM temperature again, right? Because it will couple the spin temperature with the Lyman alpha color temperature, but Lyman alpha color temperature is same as same as ideal temperature. So now again see this line is going down because of the Lyman alpha coupling. But then when they are fully coupled, IGM temperature and steam rate temperature, speed temperature both is increasing. So now I think we understand all the important processes that determine the evolution of spin temperature and differential brightness temperature. Yeah. Okay, so this goes down because so if you remember spin temperature equation, the spin temperature inverse is equal to steam rate temperature plus alpha IGM temperature inverse. Now, if X alpha is very high, let's say more than 100 maybe, then that term in this equation, that term dominates. So spin temperature will be exactly same as IGM temperature. So that's what is happening. So see, this is IGM temperature, this blue line and red line. So this spin temperature is actually trying to catch this IGM temperature. Because of that, line of the coupling. So now once they are coupled, fully coupled, so IGM temperature and spin temperature are same. But now this X-ray photon actually are coming in. And they are actually heating up the intergalactic medium. So that's why this rise, because of this X-ray heating or any kind of heating, maybe due to cosmic ray, maybe due to primordial magnetic field, they can also heat up intergalactic medium. So I haven't discussed that, but there are many possibilities, and you can actually explore that. Okay. So that is the full picture, and this is the exact ups and downs path that really Prof was saying, and also Willis was explaining. This kind now this depends on, of course, this is not unique. This depends on the source model and also various factors. It's very uncertain, and that's why we need to constrain those things using observations. So hopefully we'll know in exact form in few years. So yeah, so that's all. Thank you. If you have any question, you can ask now or ask